So let's go on a quest to find the ultimate building blocks of our universe, atoms and molecules. We're talking about the fundamental stuff that makes up everything you can see, everything you can touch, and even things you can only imagine. And it all kicks off with a question that has puzzled people for thousands of years.
It really does start with this simple but kind of mind-bending question. Picture this. You take a piece of gold and you cut it in half. Then you take that half and you cut it in half, and you just keep going. Could you do this for the rest of time? Or would you eventually hit a point where you have a tiny fundamental particle of gold that you just can't cut anymore?
You know, this question wasn't first cooked up in some fancy modern lab. Nope. It was born in the minds of ancient philosophers. For literally thousands of years, people have been wondering about the true nature of all the stuff around us.
And what's really fascinating is that brilliant minds, thousands of miles apart, were having the exact same thought. Around 500 BC in India, the philosopher Maharishi Kanad suggested that if you keep dividing matter, or padarth, you'll eventually hit an unbreakable particle he called a parmanu. And at pretty much the same time, all the way over in Greece, a philosopher named Democritus came to a similar conclusion, and he gave it a name that stuck, atomos, which literally means indivisible.
But here's the thing. For more than 2,000 years, this was all just a thought experiment. A beautiful idea, for sure, but it was all based on logic, not on hard evidence. There was just no way to prove these tiny little particles were real. Well, that all started to change when scientists began finding the first real experimental clues.
Okay, so let's fast forward a bit to the late 18th century. This is when science really starts to shift from just thinking about things to actually measuring and experimenting with them. And scientists started noticing some really consistent rules about how matter behaves.
Think about a campfire. You've seen this, right? You start with a big, heavy log of wood, and after it burns, you're left with this little, light pile of ash. It really looks like most of the wood just vanished into thin air. So the question is matter actually being destroyed here?
Well, a French chemist named Antoine Lavoisier proved that the answer is a big no. He showed that if you could somehow capture and measure everything, the wood, the oxygen from the air that feeds the fire, all the smoke, all the gases, and the ash, the total mass you start with is exactly the same as the total mass you end with. Matter just changes its form. This became the first major rule of chemistry.
All right, so here's the next big clue the scientists stumbled upon. Does it matter where a substance comes from? I mean, is the water flowing in a river chemically the exact same stuff as water you could make in a lab by combining hydrogen and oxygen? And it turns out the answer is a resounding yes. They are absolutely identical. A scientist named Joseph Proust discovered that any pure compound, no matter where you find it, always has the same elements mixed in the exact same proportions. Water, for example, is always made of 1 part hydrogen to 8 parts oxygen by mass. Always. It's like a universal recipe that never, ever changes.
So now we've got 2 huge clues. 1, matter is never lost, it just changes. And 2, compounds always follow the same recipe. But why? What could possibly explain these rules? Well, the detective who finally cracked the case was an English schoolteacher named John Dalton.
Meet John Dalton. And get this, he wasn't some famous aristocrat with a fancy lab. He was born into a poor family back in 1766 and actually started his career as a teacher when he was just 12 years old. He was simply a brilliant, incredibly curious person who saw the connections that everyone else had missed. Dalton's theory was a total game changer. He brought back that ancient idea and said, okay, everything is made of these tiny particles called atoms. He proposed they can't be created or destroyed, which, boom, perfectly explains why mass is always conserved. And he said they combine in simple whole number ratios to make compounds, which is exactly why water always follows that same recipe. In one brilliant move, he connected all the dots and turned an ancient philosophy into a real, testable scientific theory. So Dalton basically hands us the rulebook for how chemistry works. It's a revolution. But you know how it goes, right? Every great answer just opens up a whole new set of questions. Like if these atoms are real, just how tiny are they? And how on earth do you weigh something you can't even see?
Just think about it. Atoms are the most basic building blocks of, well, everything. They're like a single brick in a giant skyscraper, or 1 grain of sand in a massive anthill. The atom is that fundamental unit. But the scale we're talking about is almost impossible to wrap your head around.
Let's try to get a sense of it. A grain of sand is pretty small, right? We're talking about a 10,000th of a meter across. Tiny. Okay, ready to go smaller?
A lot smaller? A single molecule of water is about 1/1000th of a meter. That is 10,000 times smaller than our little grain of sand.
And believe it or not, we can go even smaller. A single hydrogen atom, one of the smallest, is about 1 times 10 billionth of a meter. You could fit millions and millions of them on the head of a pin. They are truly unimaginably small.
For centuries, the idea of actually seeing an atom was pure science fiction. But today, we can. With amazing modern tools like scanning tunneling microscopes, we can create these incredible images of surfaces. Take a look at this. What you're looking at is the surface of silicon. And each one of those little bumps, that's an individual atom. The ancient idea is now something we can see.
Okay, so they're real. We can see them, but how in the world do you weigh something that small? You obviously can't just pop one onto a scale. So scientists came up with a really clever solution. To understand it, let's imagine a fruit seller who doesn't have any standard weights, like pounds or kilograms. How could they sell their fruit fairly? Well, they could just take a big watermelon and decide, okay, this watermelon has a mass of 12 units. Then they cut it into 12 perfectly equal slices. Each one of those slices is now their standard weight, 1 fruit mass unit. So if they want to sell an apple, they can put it on a balance scale and see how many watermelon slices it takes to balance it out. They're measuring everything relative to something else.
And believe it or not, that's pretty much exactly what chemists do. They just needed a watermelon. They chose a common atom, carbon-12, and defined its mass as exactly 12 atomic mass units. So 1 atomic mass unit, or U, is simply 1/12 the mass of that standard carbon atom. And now every other atom on the periodic table is measured relative to that standard.
So, let's pull back and look at the bigger picture here. We've gone all the way from an ancient philosophical question to a concrete system for measuring the very building blocks of reality.
And that, right there, is the most incredible part of this whole story. The air you're breathing right now, the device you're watching this on, you yourself, it's all just an incredibly complex arrangement of a few kinds of simple, invisible atoms, all combining in predictable ways to create, well, everything.
Dalton's theory was a monumental leap forward. It explains so much, but it was all built on that one core idea from the ancient Greeks, that atomos means indivisible, that the atom was the end of the line. But what if? What if he was wrong? What if you actually could split the atom? What smaller, stranger things might you find hiding inside? Well, that's a story for another time.